Tonight we're fortunate to have the CTO and co-founder of Mesosphere. He's here to tell us about something many of us are familiar with, automation, in particular how we can use Mesosphere to help us move common open source services and microservices as an on-service model with high level of automation and control. So please help me welcome Tobi Knaup and his talk, Automating Microservices and Data Centers Anywhere.
Thank you. Well, thank you for the kind intro, and thank you for the opportunity to speak here. If you haven't tried the beers yet outside, they're really good. Yeah, a little bit background on myself. So, I've been playing with Linux servers for a while. I started, when I was a teenager, I started a company with a friend where this was in the 90s, and people in my hometown in Germany, heard about the internet for the first time and were wondering, where can I buy an internet? So lots of small and medium-sized businesses there that wanted a website, that wanted an email address. And it was really hard for them. They didn't know how to even think about that. And so, we built our own Linux servers. We put them in a data center. We ran them. We hosted the websites there. So that's, the first time when I got my hands on system administration. And sort of from an early age on, on one hand, I enjoyed system administration, but on the other hand, I didn't like to get paged. So I always try to automate as much as I can so my pager wouldn't go off. And so from the very beginning, even though we didn't need two servers, we bought two servers. So one could take over if the other one would fail. And we linked them together with a serial cable so we could log into the console in the other one. So those were my early experiments back in Germany. What year? It was in 98, I think, is when we started, yeah. This friend of mine and I, we actually both moved to the Bay Area around the same time and then started Mesosphere together. Before then, so Mesosphere is about 5 years old. We moved here about 10 years ago. Before then, we had different jobs. He worked at Twitter. I worked at Airbnb. Both building infrastructure at those companies, both wearing pagers. And as you can imagine, I don't know if any Twitter or Airbnb employees here or former employees? No. But as you can imagine, two very fast-growing companies. Things break all the time. And kind of the same mindset. We wanted to automate everything. And we found this open source technology called Apache Mesos that actually another friend of us, Ben Hindman, had created in Berkeley. It was his PhD project, and they were looking at building a substrate for cluster computing, so a system that allows you to build and operate other distributed systems on top of it. So kind of extracting all the common patterns from distributed systems. And so we were using that at Twitter and Airbnb to run the infrastructure there, and then it felt really powerful to us. It really felt like we had a tool that made our lives a lot better, and we would get paged a lot less because it would restart things automatically. And so we decided to create Mesosphere, the company, to bring this open source project to everybody. And we created a product around it called Dcos. That's what I'm going to show today. I always like to compare that a little bit to Linux. So Mesos is a little bit like the Linux kernel. It's a kind of a low-level piece of software. It's very powerful. But if you're using a Linux kernel-based system, you're probably not interacting much with the Linux kernel yourself most of the time. You're using software that uses the Linux kernel. And so Dcos is a little bit like a Linux distribution, right? It gives you all the other tools that you need around the Linux kernel to do useful things with it. And some of the useful things that people do with Mesos and with Theseus are DevOps and DataOps. This is what we did at Airbnb and Twitter. We ran lots of microservices at Airbnb, and then microservices at Twitter and data services at Airbnb. So DevOps is a term you're probably all familiar with. DataOps, to say I'm not the biggest fan of the term, but people have started using it more to talk about how you run complex distributed data services in production and how you automate those. So that's what I want to talk about today. I have a couple slides, and then I want to actually show you what it looks like. So we're going to be playing with the terminal and some GUI too. But just a couple of slides to kind of set the stage. So, today, if you're deploying apps into production and you're starting from scratch, you're probably doing that with microservices. That's the pattern that's popular now for architecting applications, gives you a lot of, elasticity. And so when you deploy these apps into production, typically today that's done with continuous integration and delivery software, things like Jenkins or Spinnaker or similar things. And then those microservices end up in production, so they're running, on a cluster, and everyone's happy, right? Now, unfortunately, there's a lot of complexity under the hood to make this work, right? This is what it looks like from a developer's perspective. It's very easy. But just setting up a continuous integration delivery pipeline that scales with the number of developers and the number of jobs that need to run and scales elastically with the workload on it is pretty complicated. And now there's a little bit of a twist because microservices don't give you an entire application. What it actually looks like is more like this. So, here I'm showing like a connected car application where you have a car and the car sends some data like what is its speed and what the sensors are saying, or if it's a connected car, it now has cameras and LiDAR and all those things. And the driver also has a mobile app. And so there's all these different microservices that they can use, like I can track my car, I can look at traffic, remote diagnostics so that I know when I need to take it to the shop, and so on. So those are all the microservices, but then there's this whole universe of data services that's running also, right? The data services that are backing these microservices. So various different databases, message queues, machine learning that does the self-driving, big data, lots of storage systems. So it's very complex, right? And lots of interdependencies between all the different services. And then a lot of applications that I see these days that I'm working with customers on, they are actually split between data center, cloud, and more commonly now also edge locations. Various forms of edge locations, but we've had edge locations for a while, CDNs, right? That's how you move things close to the user for low latency. But the amount of things that people are running on the edge it's increasing. They're becoming more complex. So point of the slide, is to show there's a lot of complexity here, right? And if you're adopting cloud-native applications, so microservices, container orchestration, that in and of itself brings more challenges for ops. Because first of all, so you have many more things to manage, right? It's no longer a 3-tier application that has only a few pieces. Some of the microservice deployments might have hundreds of different microservices that all need to talk to each other and need to be able to discover each other and so on. They have dependencies. There's more movement, right? Containers, Linux containers, they start up quickly, and the CI/CD model allows or it enables developers to deploy very often. So there's just generally a lot of movement in the cluster, right? Lots of apps spinning up, new versions getting deployed, things scaling up and down. Which is the next point. There's a lot of variance, right? So people are scaling their infrastructure and their applications elastically with the traffic. And there's also more abstraction layers now in there, right? A container orchestrator abstracts away the underlying infrastructure, so it gets a little harder to debug things. And just generally, these are distributed systems. Distributed systems in and of themselves are very complex, and when they fail in complex ways. And so unfortunately, many of the tools that we're used to for system administration, they kind of break down in this environment, right? We no longer have the luxury to say, all right, this application that I'm running, I know it's always running on this server with this IP address. That just isn't true anymore. So let's talk about fast data services, the services that DataOps is for. what's been happening, so everybody knows Hadoop, right? It's been used for a little over a decade now for batch processing, right? So you collect a bunch of data over a week or over a day, you run some reporting, you make decisions based on that. But over the years, now the batches have become smaller, micro batches, and now there's a lot of real-time systems that people are building. And these require complex infrastructure. So, examples of those are connected cars again, right? You have data coming out of the car all the time. This could also be banking transactions at a large bank. This could be at Twitter, where they want to look at all the likes and who you follow so they can serve you better ads. And so to build a real-time data pipeline, a popular pattern that we see a lot is what's called the SMAC stack. So it's the initials of all the technologies that are involved here. So it starts with events of some sort, coming from sensors or devices or just a click stream on the website. You ingest that in a message queue like Kafka. You analyze it in real time with something like Spark, a stream processor. You want to store that data for the long run. If it's structured, you're probably using something like Cassandra or Elasticsearch. If it's unstructured, probably it's something like HDFS. And then you need an application stack to build applications around that data. So every one of these pieces is a distributed system. So lots of work to do on the operations side, right? And what makes it challenging too is that every one of these distributed systems has its own characteristics and topologies. So Cassandra is a ring. It has nodes that all, they have different buckets of the overall hash space, but essentially the nodes all have the same node type. But if you have something like HDFS, it looks a lot more complicated. HDFS has many different node types. It has multiple journal nodes. It has an active name node, a standby name node, and then many data nodes to store all your data. And so each one of these components needs to be treated differently. First of all, when you deploy HDFS for the first time, you need to deploy these nodes in the right order. When you upgrade HDFS to a new version, you need to do that in the right order. When you have failures in the cluster, every one of these different nodes has a different recovery procedure, right? There's a lot of complexity there. Any HDFS administrators in the room? Yep. You probably know what I'm talking about. Yeah. So just lots and lots of complexity there. So yeah, the challenge really is that every one of these systems and modern enterprise applications consist of a lot of these different things. They each have their own operational characteristics, and that makes it really hard. You really need to become an expert in every one of these technologies or build individual teams for each one of these technologies. And so what are the tasks that we need to do for these systems? Well, they're not different than other system operations tasks. We need to, every now and then, update the configuration, right? Change JVM settings or other configuration. Binary upgrades, right? Upgrading these things to a new version. Backup, restore, restart. Monitoring the progress of any operations like an upgrade. Debugging anything that gets stuck at runtime and recovering from failure, right? If you lose nodes or anything else happens. So pretty common set of tasks, but again, it's very different between those different services. Now, you can kind of go the naive approach to do this and have a different pool of servers for each one of these workloads. And then you use your favorite configuration management tool. If you're running something large, it's more likely that you have different teams that manage these different services. And so you're using a bunch of these tools. So you're doing this n times. So it kind of becomes a mess. You have a bunch of servers that are not being really utilized. You have a lot of different tools. You have different teams running the different services. Just a lot of complexity. It's not a simple approach. All right. So I talked a lot about problems and challenges. Now I want to talk about some solutions and show you DCOS. Who's familiar with DCOS? Quick show of hands. 1, 2, 3. OK, a few people. So DCOS is is a system that, it runs an agent on every one of your machines, whether they're physical machines that you run in your data center or they're virtual machines on the cloud. And it takes all the resources on those machines, so CPU, memory, disk, GPU, anything else that you have in terms of hardware resources, and essentially exposes it as a single pool of resources, right? And then when you run applications like any of these, you no longer tie them to individual machines. You essentially submit a spec that says, here's how much CPU, memory, and disk, and other resources this application needs. And then there's a scheduler in DCOS. There's actually multiple. We'll get into that. That figures out, what's the best machine to place this workload and run it. So there's sort of, we call it a resource offer. DCOS offers system resources to the different workloads periodically, and then those workloads decide, all right, this matches my requirements, so I'm going to run on this machine. So you end up with a single pool of machines running many different workloads. We use Linux containers to isolate the different workloads running on the same machines. So you have, CPU, memory, and other system resources isolated. But this model has a lot of benefits, right? So first of all, you don't have to do this mental math in your head anymore or maintain that big spreadsheet that tells you which servers are running which applications. It's dynamically managed by DCOS. It also generally reduces a lot of snowflakes in your cluster, right? Typically, when you deploy this, you have one or maybe two or three different hardware SKUs, right? You might have a storage-heavy node and a compute-heavy node, but you move away from this model where you have a 12-core machine here and a 16-core machine there and a 24-core machine there. You can run with much fewer hardware SKUs and just let DCOS bin pack all of your applications onto those machines. It also helps with high availability. I'll show that in the demo. So if you lose an entire machine, those workloads can easily migrate to a different machine, right? Because DCOS knows what the spec is to run this thing. It knows the memory and CPU and other requirements. It knows where to get the code, where to get the Linux container that includes the code. And we'll talk about a component in a bit that we call application-aware scheduler. So this is essentially a runbook as code that can be automatically executed. So if you lose a machine, this application-aware scheduler will go in and run the recovery runbook that figures out how to reprovision that node that was lost. So really high degree of automation. Yeah, this shows kind of the architecture, what the stack looks like. This is DCOS on the left here, and this is there's other container orchestrators that are really built for microservices, and the way that those work is so you have hardware at the bottom, you have your machines, whether those are virtual machines on the cloud or physical in your own data center. There's a runtime or an agent that runs on all these machines, and in a microservice-oriented container orchestrator, you have this resource management. So this, how much CPU and memory do I need? Which application gets it? That's resource management. And then the container orchestration. So how do I do a rolling upgrade of a containerized application and so on? That's container orchestration. That's very much focused on microservices in most container orchestrators. So if you're running your data services here too, you still need to figure out yourself how to operate those, right? Using Chef, Ansible, and all these other tools. So it's manual, and you end up with these hardware silos that have low utilization. In the DCOS model, it looks a little different. So you also have a runtime, but then we split the orchestration and the resource management into two. So there's a core piece that's actually Apache Mesos that does the resource management. So figuring out which workload gets which resources. But then we have these pieces that we call application-aware schedulers that are, a piece of software that have this runbook built in. So there's a generic container orchestrator for any microservices that you built yourself. But then for many data services, like Kafka, like Cassandra, like Spark, the workloads that I just showed, and many more. There's a piece, a scheduler that's purpose-built for that workload, that knows how to deploy Cassandra, that knows how to fix it when it's broken, that knows how to upgrade it, and so on in a highly automated way. By the way, if you have any questions, feel free to jump in. Yes, there's one.
Why do the history to just have two separate orchestrators for microservices on the data, right? So why can't they do the same? It's doing similar thing, but what's the main purpose of having two different?
Yeah, why multiple schedulers? So let's pick a concrete example, right? When let's say you have a microservice and it runs on 10 different nodes. The developers updated the code, so you need to roll out the new version of that microservice. Because microservices are stateless, the container orchestrator can just go in and restart them in any order. You can do a rolling deploy, for example, restart them one after the other, make sure they're healthy, and you're good because they're all the same, right? All 10 instances are the same code and they're stateless. Try to apply that same model to an HDFS cluster, right? You're probably going to end up with a broken cluster because you updated the data node first and then the name node second, and you're supposed to do it the other way around, right? So those data services each have their own topology, and when you perform admin tasks like that, you need to do an upgrade the right way. Does that make sense? Okay. Any other questions? No? Okay. So this is very fine print. You probably can't read this, but low resolution projector. What this basically says, so there's a row here that says application resourcing requirements, and then there's one that says application orchestration requirements. Basically, this is just to show that different kinds of workloads have different requirements, right? So in terms of the resources, Kubernetes, which is a workload that runs on top of DCS, great for stateless microservices. Those tend to be CPU or memory intensive, but because they're mostly stateless, you usually have a lot of storage for those workloads. On the other hand, HDFS, a distributed file system, right, very storage heavy. Or Spark here, which is an analytics engine, also for deep learning. Nowadays, a lot of folks want to use GPUs for that. So very different hardware requirements, right? And then also very different orchestration requirements. It's what we just talked about, the example, right? For microservices, you can restart them in any order. For HDFS, you need to be a little more careful, or a lot more careful. And for Spark, that's batch jobs, right? You spin up a bunch of batch jobs, you wait for them to finish, and you free up the resources afterwards. So those are examples of why you need these application-aware schedulers. Okay. So what does DCOS data service orchestration provide to you as an operator? So as I mentioned, those packages come with these workload-specific application-aware orchestrators, but they give you a couple more things that are really cool from an ops perspective. You get a consistent API for operational tasks. So the way you do an upgrade of a Cassandra, or you trigger an upgrade of a Kafka, it's a similar API call. Basically just a different application name, and the configuration has a different format. But it's very easy to automate around these things because the API is consistent. You also get a command line tool where you can easily, with one command, trigger those updates. I'll show you what that looks like in a second. And then I already talked about this. A lot of the operations you usually have to do yourself are highly automated here. Again, one of the reasons why I started this company is because I don't want to get paged in the middle of the night. With this high degree of automation, it's going to happen a lot less. Yes?
How long does it typically take teams using DCOS to come to that part? Right? There's always a
Yeah.
cost, time,
Yeah.
range.
So the question is, how long does it people take to adopt DCOS, essentially? Yeah. To get to autonomous operations. Yeah, I'd say fully autonomous operations is still in the future. Still some work to do. But a lot of the very common failure scenarios are already automated. So, something runs out of memory and it crashes. Let's restart it. What I'm going to show actually for Kubernetes is if you lose the node that runs its data store, that'll get recovered automatically.
We're asking more
Yeah. Yeah. Yeah, fine-tuning DCOS itself or the workloads? Yeah. I'd say it really depends on what's running on top. We've had folks that moved into production with a fairly complicated application in 2 to 3 months. Sometimes it's a little longer, 6 months or so. This really depends on honestly in large part also the sort of the team culture or the company culture, right? Are they ready to adopt microservices and distributed autonomous operations like that? Yeah.
Just to follow on Rob's question, does it have any relation to scale the application?
Does it have, sorry, can you say it again?
So like, for example, the ramp up of the basically.
Oh, does it take longer to ramp if it's a larger scale? Yeah, I think, yeah, I'd say, definitely, putting 10,000 servers in a data center takes a lot longer than, but you can do it with a lot fewer people. So at Twitter, for example, the number that they shared publicly is they have one system administrator for 10,000 servers. So it's not a lot. So you can really automate to a high degree. This next one I think is really important. So automation is great, but we don't want to have a black box system that we don't understand and that does things where we can't intervene, right? You want to have safeguards, so checkpoints that when something goes wrong, you can run some smoke tests or whatever you need to do, and then also manually intervene. So there's also tools there that allow you to do brain surgery is what I like to call it always, because we all know those things will happen, right? Death by automation happens too, yeah. Absolutely. So that's why we included those tools so you can debug things when they go wrong. All right, so that's it for the slides to kind of set the stage. Now let's play with some tools. Yes. Yeah. Yeah. So let me talk about that. So there is 2 ways to run things on DCOS. I'll repeat the question, yeah. So the question was, so we support some well-known workloads like Kubernetes and Spark and Kafka and others. What about workloads that are not as well-known? So if they're microservice workloads or they have a fairly simple architecture, you can just put them in containers and actually launch them with what's built into DCOS. For things that are more complicated, say you have another distributed database that's not supported yet, the SDK that we use to build these application automation pieces is actually open source. So you can find it online on GitHub, Mesosphere. There's instructions there, so you can actually build your own for your own bespoke database. Yeah. Any other questions?
So what is the baseline operating system you are going to use? Is it Linux or any hybrid?
Yeah. So question was, what's the baseline operating system? It's Linux today, so any modern Linux distribution. I say modern because a lot of the container stuff requires features that have been added to the Linux kernel recently. So a recent kernel is pretty important. Yeah, so that's what most folks use. Yeah, so the ones that are officially supported today, CentOS, Red Hat, the 7.4. CoreOS Linux is also supported. Ubuntu we don't officially support as Mesosphere, but it works. Who takes care of patching the OS? That would be up to the user. Yeah. So where DCOS kind of sits, it puts an agent on top of Linux, and then runs everything on top of that.
So whatever we download Kubernetes software, I can directly install on this, or does it have any other special?
Yeah, so the question was, when you download Kubernetes, can you install it on there? That's actually the first thing I want to show. We'll see what that looks like, yeah. It is Linux and Docker containers, yes. In fact, so Docker containers are one of the types of containers that we support, obviously super popular, but we also support other container types. We have a pluggable container runtime, support the Docker engine, and we also have our own container runtime, which is called UCR, Universal Container Runtime. So it supports Docker images, it supports our own containers, and the team is working on OCI support, also the open container spec. So yeah, supports multiple container formats. All right. Log in here. So this is a cluster that I provisioned on the cloud. So part of the meetup title, I think, was to run all these workloads anywhere. So anywhere means any cloud provider, your own data center, physical servers, bare metal, virtual servers, you name it. This one just happens to be on a cloud. And you can look at the nodes here that make up this cluster. So I'm running this on Google Cloud, US West 1 in this case. You can see the region and the zone. Everything's empty right now, nothing really running. And when you look at the dashboard, you can see we don't really show you individual machines. You can go to this node view and look at them, but really, we want you to think about the entire data center or cloud deployment kind of like a single computer, right? Not worry too much about individual machines. So, this is the dashboard. We'll get to the services view in a little bit, but I want to show you the catalog. So what Dcos allows you to do is to run a large number of workloads from this catalog with really an experience that's similar to a public cloud. Right? If you go to an AWS or Azure or Google Cloud, you can, with a few button clicks or an API call, provision a database. Right? It's a really great experience. The only challenge with that is that these things don't work in your own data center, right? And when you do them on one cloud provider, that same automation doesn't exist on a different cloud or again in your data center. So if you need to run things on multiple types of infrastructure, it's not really a great option. But since DCOS runs everywhere on any cloud and on your own servers, you can use that to get a cloud-like experience on any infrastructure. All right, so we're going to start with Kubernetes because it's very popular. Look at my script here. So what I want to do is I want to show you how to install an entire Kubernetes cluster, which consists of a lot of pieces. We'll see what all those pieces are. With just a few commands. And this is important, in a highly available, secure, and production-grade way. So it's going to be a cluster that has 3 of each of the master components. It's going to have TLS enabled. It's going to have ACLs and all that, everything that you need to put it in production. So you can do this from the UI. You can just click on it here. Click Review and Run. Change a lot of settings here. Very Kubernetes-specific settings, right? Different authorization modes, the network that it uses, etcd, the data store of Kubernetes. Change the settings here. And so for every one of the services here in the catalog, you can change all these settings that are specific to that service. So while it is highly automated and easy, and we also expose the settings, right? Because you're going to have to change those. So it's not like a SaaS where you can't change anything. I sometimes like to call it open SaaS, right? It's almost gives you the ease of use of SaaS, but you can go in and change all the settings. All right, so what we need to do here first is a couple of command line things. First of all, I'm going to install the Enterprise CLI. So there's 2 versions of DCOS. There's an entirely open source and free version, and then there's an Enterprise edition, which adds additional features, mainly around security. Yes?
Wasn't there a CLI option in the UI to install it?
There is a CLI option in the UI, yes. So you can it basically just makes what I just did much easier. So you can go in here and say install CLI, and it just gives you the commands that you need to do. Oh yeah, that's right. That's the same thing that I just did, essentially. You can do all these installs from the GUI or from the command line. So you see all the packages that you see in the catalog. You also can do from the command line. So Dcos Enterprise CLI, and I just did package install Dcos Enterprise CLI. Same package. Same package, different interface.
So will the installer know once it's installed that it's installed?
If yeah, so you this is a little bit tricky. You always need to install it on the cluster and on the CLI. In the Dcos Enterprise CLI's case, you don't need to install it on the cluster because it just talks to APIs. But for the packages, you'll see that when I install it. So if you're running this command, for example, which says Theseus package install Cassandra, if you run that from the command line, it'll put Cassandra on the cluster and you get the Cassandra CLI. But if you were to install Cassandra from the UI, that puts it on the cluster, obviously, but not in your CLI. So you'd have to run the package install Cassandra -- CLI in addition to that to get the command line also. Does that make sense?
Yeah. The other question is, when you install it from the CLI, does the UI know that it's been installed and tell you?
So for Cassandra and any other workload, yes. So you run, if you do package install Cassandra or package install Kubernetes, which we're going to do right now, it installs both CLI and cluster. But if you do it from the GUI, only cluster, because the GUI can't go to your machine. And
So if you go back to the UI for a second,
yeah,
and then click on the CLI.
yeah, this doesn't do anything. Because the CLI is a CLI, it says CLI only package, so there's no install button.
Okay.
It just tells you what it is, basically.
Is that how it looks once it's installed, or that's just coded?
This is just what it looks like in the catalog. So these are not installed, right? This is just what's available. What's installed will show up under services here. Yeah. Okay, so I have the Enterprise CLI, and so what that allows me to do now is to do a few security things. So I want this Kubernetes cluster to be secure out of the box. So what I'm doing here is I'm creating a service account. I do that. And Kubernetes will use this, this service account to talk to DCOS, right? To authenticate to DCOS, because we don't want just any software talking to a cluster and doing things. We want to authorize it. So I created this public and private key pair. I created the service account. The next thing I will do is, so the service account needs a private key. So I'm doing DCOS security secrets create service account secret. So it basically takes this private key that I just created and stores it in the DCOS secret store in an encrypted way, from which we can send it to the different nodes that need it in also an encrypted way. So safe place to store all these secrets like private keys. All right, so that's created. And now the last command, I'm cheating a little bit, just for keeping the demo short. Don't do this in production. So I'm adding this user Kubernetes that I just created to the super users group. Don't do that in production. You want to set more fine-grained permissions in production, which you can. Just keeping it short. All right, so we have the service account. We have the service account secret. Now we can deploy the cluster. So what I'm going to do, I'll first show you what it looks like from the or I already showed you what it looks like from the GUI, Kubernetes. But we're system administrators, so we like the command line, so let's do this from the command line. Instead of doing all these settings in the GUI, I can say DCOS package install Kubernetes. I can pass in options. I'll show you what that options file looks like. And then I can specify the package version, right? So Kubernetes and any other software, there's different releases all the time. You might want to pin to a different version. So what I'm doing here on purpose is actually I'm using not the latest version because I want to show you what an upgrade looks like. And then I'm passing in this options file. I'm going to kick this off right now. Oops, I'm in the wrong folder. All right. Yes, I want to install this. Okay, so you can see it's installing an app on the cluster and it's installing a new CLI subcommand for Kubernetes. So when I talked about consistent API and CLI earlier on the slides, this is what I'm talking about. So you're getting a Dcos Kubernetes CLI command that you can now use to interact with Kubernetes that's running on your Dcos cluster. I'll show you the options file real quick that I used here. So, just some simple configurations. It says use the service account that I just created, use the service account secret that I just created. I want a highly available Kubernetes cluster, so this is literally all you have to do, set this to true, to get 3 of each of the master components instead of 1. And then I want to run 3 nodes or kubelets to run my workloads. So that's what's in the options file. Okay. Going back to the GUI so we can look at how this thing is running. So you see a new service, Kubernetes, now spinning up. And the first container that's running here that's just called Kubernetes, that is this application-aware scheduler. Let's look at this thing real quick and see what it does. You can look at logs from the GUI here. You can also do that from the command line. And so you can see it's logging a bunch of stuff. What's it doing right now? It's running an etcd peer. It's processing offers. There's a status update that says task running for etcd peer. So it's starting to provision the entire Kubernetes cluster. And so as I mentioned earlier, there's for any of these workloads, there's a certain order that you have to go through to do this, right? If you go back here, you can see some etcd tasks spinning up. Let's look at this deployment plan, actually, that it runs to bring up this cluster. So we can run this command here. Make some room. Dcos Kubernetes, right, this new CLI command that we just got. Plan, show, deploy. And this prints out in this kind of tree view what's going on. So at the top level, this plan is called deploy. It's in progress right now. And then within this plan, there's what we call phases and steps. So the next level down is a phase, etcd, API server, mandatory add-ons, and so on. And then within each phase, there's multiple steps. That's these guys here. And so you can follow the plan along, right? You see these 2 etcds, they completed. This one has started to deploy. These other ones are still pending. And there's different deployment strategies that a package owner or package maintainer can specify, right? So in this case, the etcd nodes, they get deployed in a serial order. Other types of workloads you might want to deploy in parallel, right? Like the API servers, they're actually stateless, so they get deployed in parallel, right? So whatever deployment strategy makes sense for the different pieces of the system. You can refresh this a few times. Question? There is an API to get that status, yeah. So everything I'm doing here, whether it's through the GUI or the CLI, there's an API behind it that you can automate against. I'm sorry, say it again? There are dependencies between different steps, yes, which is why, so the phases and the steps let you model that, right? So this API server phase depends on the etcd phase. So this one will complete first because we said up here deploy is a serial strategy, right? So the phases will happen one after the other. But then within each phase, you can do some things in parallel, like in the API server case. Really just depends on the package. OK, while this is deploying, I want to also in parallel kick off. Sorry, there's a question? The plan is already there.
If I have to go back and let's say change the plan, let's say I want to deploy X before Y.
Yeah. Yeah, so the plan is part of the package, right? It's built in, so when I just install package install, it comes with the package. And I mean, typically there's one recommended way to deploy Kubernetes or Cassandra and so on. So there's usually not a need to change it. But like I said, all this stuff is open source. So if you really wanted to change it, you could. Yeah. So what I'm going to do in parallel is here, run a stateful service also, because I want to start something on Kubernetes that talks to a database. So I'm going to also provision a Cassandra cluster. So similar command, Dcos package install Cassandra, --es skips the prompt.
So when we take Enterprise from Theseus, is there any server where which maintains the everything like master of all our data or all our documents? Is there any master?
Yeah, so the question was, are there master nodes in Dcos that sort of maintain the state? Yes, so it's agents run on all the different nodes that run workloads, and they're connected to between 1, 3, or 5 masters. For production, we recommend 5. If you're just testing, you can run 1. And the masters are sort of they do the coordination of where should workloads go, forward resource offers, status updates, all that stuff.
Okay, again, while setting up the Theseus on like 5 nodes or 10 nodes,
Mm-hmm.
what efforts we need to, what are the, how much package and what are the agents, or is there any documentation to follow and build a cluster?
Documentation for building a cluster? Yeah, docs.mesosphere.com. There is multiple different ways to install it. Yeah, so we provide an installer, which you can call from your favorite infrastructure automation tool, Terraform, Ansible, Chef, Puppet. But it's an on-node installer, so it sets up the node in the right way, puts all the bits in the right places. Yeah, you just call that with your favorite system orchestration tool. Yeah. So another question over here? Yes? How do you change Cassandra settings? Great question. Let me show you. So I installed this with all defaults. But if we go back to the GUI here, you can see Cassandra is provisioning now. If you find it in the catalog, it's right here. We expose a lot of settings. So this is sort of generic service level settings. What's interesting here actually is, so Cassandra has a concept of a data center and a rack, so you can run it in multiple locations. You can set that here. So we have folks that are running Cassandra across multiple clusters. Backup resource strategy. This one I really like. Enabling transport encryption in any service is usually a lot of work. It's a checkbox here. Really, really easy. And then here are the node settings, JVM heap size, and then lots of Cassandra specific settings. Authenticator, authorizer, JMX ports, number of tokens per node. There's a little help there also, a little inline help that shows you what these settings mean. And for some of these services, it's a long list, so you can really tweak a lot of settings. Yeah. So the question was, if you have 2 data centers and you want to run split nodes between them, I'm going to give a very computer science answer. It depends. Well, it depends what your expectations are around high availability, right? If you want hot standby, 2 data centers, I would suggest to run 2 completely separated Dcos clusters. You'll run Cassandra here and over there. Data center 1, data center 2, you can change that in the settings and use asynchronous replication in Cassandra. If it's more of a, you don't want hot standby, you just want a way to easily, pinpoint, deploy workloads into 2 data centers, you could also run a cluster that spans both. But obviously, if you lose one data center for a longer period of time, you might run into trouble. Right? So it depends. All right, so we deployed Cassandra. Oh yeah, let's look at the deployment plan for Cassandra. So we saw the one for Kubernetes earlier. The Cassandra one looks a lot different. It's a lot easier, actually. what you can also see here, actually, so this also gets deployed with the serial strategy. What you can also see here is actually one-off tasks, right? Most of what you saw here and for Kubernetes are daemons that we're starting, right? Like this node 0, node 1, node 2. But for Cassander, we also need to run a one-off task that inits the system key spaces. So that runs on node 0 as soon as it's provisioned. And that's just a run to completion task. It's not a daemon. So those things are part of those packages too. OK, so this thing is now complete. I'm going to run a few Cassandra commands real quick to just create a table so I can show you an application. Dcos node SSH is a pretty cool command. Also just allows you to SSH into the cluster without having to know any host names or IP addresses. Just running a Cassandra client in a container. And then I'm just going to run these two commands to create a table. Extracting. While this is extracting and doing all kinds of other stuff, let's look at our Kubernetes cluster. So you can see there's a lot of stuff running now, right? Kubernetes is a pretty complex system. It provisioned 3 etcd peers, right? We wanted a highly available system. You can also see 1, 2, 3 API servers. Let me actually filter this so it's a little easier. So API servers, 3. You can see 3 controller managers. It's another master component in Kubernetes. And then you can see 3 schedulers, another master component. And also 3 nodes or kubelets. So it provisioned everything that we wanted. Pretty cool. So let's run these 2 things real quick. All right, done and done. All right, so with just a few simple commands, we have a fully configured Kubernetes cluster. We have a fully configured Cassandra cluster. Now let's start an application. Or first of all, I want to show you that I was not cheating, that we actually have Kubernetes running. To do this, I need to do a little bit of trickery just to tunnel to the API server in Kubernetes. And then Dcos Kubernetes also comes with this neat little command that just sets up your kube config so you can talk to Kubernetes. What's really important to note here is this is 100% open source Kubernetes, right? It's not, Kubernetes on Theseus is not different than if you set it up yourself. It's not hidden behind any APIs. You talk to it with the same tools like kubectl, the standard command line utility, kubectl get nodes. You can see 3 nodes of Kubernetes running with the version that we specified earlier. Use all the same commands, like you can do kubectl, or kubectl is what it's called, proxy, to proxy to the Kubernetes user interface. Let me show you that. And it's just the standard Kubernetes user interface. What I should also mention is that actually we install a few useful add-ons also. So you can see there's a couple things running already, a couple pods running on this Kubernetes cluster. They're installed out of the box. So for example, this dashboard that we're looking at is pretty useful. There's a metric server installed by default that collects metrics in kubedns, so you have DNS resolution. So the goal is really to just make it work out of the box. OK, so we have Kubernetes running. Let's run something on Kubernetes. I have a simple application that just will talk to Cassandra. It's a simple microservice that just stores some data in there. So kubectl create, standard command for creating a deployment and a service in this way, in this case. And I can watch it do things. So you can see some of them are already running. So one is still creating. And then what I want to show you is how Kubernetes workloads and other workloads on DCOS like Cassandra can talk to each other, right? So for microservices, service discovery and just connectivity is always kind of a challenge. And it's also kind of a challenge to connect things from things running on Kubernetes to running outside of Kubernetes. But we've made that really easy. So if you take this pod here, for example, and say, describe pod, this one, a few things I want to highlight. So you can see the IP address that this pod has. So Kubernetes gives every pod its own IP address. This IP address is from a pool that is managed by Dcos. I'll show you that in the UI. If we go to networking, networks, you can see this 9.network is managed by Dcos, and Kubernetes draws its IP addresses from that pool so that it can talk to other workloads in the same cluster. Yeah, I think this belongs to HP. It's a demo. And the other thing I wanted to highlight is this here. So this is an argument that's sent to the container -- Cassandra host. It's just a command line argument that my microservice understands. And it uses this host name that is auto-generated by Dcos to find Cassandra. This actually uses the Dcos layer 4 load balancer. So it's a host name that will always resolve for as long as Cassandra is running, even if the Cassandra nodes move around in the cluster. That layer 4 load balancer, it uses a virtual IP, and it maps that to the actual host names behind the scenes, so that clients don't need to use any special service discovery system or anything like that. It's just DNS. And you can see these endpoints in the GUI, actually. If you go to Cassandra, you go to endpoints, this is where you would find it. Okay, so we started something. We started Kubernetes. We started something on Kubernetes. We started Cassandra. The next thing I want to show you is, oh yeah, let's do something bad. How about that? Let's destroy something. It's my favorite part. So Dcos Task shows you all the tasks or containers running in the cluster. A little bit hard to see with the resolution here, so let me grab for etcd. That's the one I'm interested in. So you can see the 3 etcd peer tasks. Dcos also gives you a useful tool to attach to any of these containers running in the cluster. I'm a big fan of debugging things in production when they're broken instead of trying to reproduce it on a different cluster, because there's just so many issues you can't reproduce. So you can connect a terminal to this container. And I'm going to use this to do something bad in this case. I'll go in and just kill the task in the container, kill the process. Obviously, this is a very dangerous tool and should be used carefully and only by people that know what they're doing, which is why we put an access control system in front of this. So as an administrator, you can decide who gets access to these powerful tools and who doesn't. So now I'm actually in the container. If I list my processes, you can see there's not a lot of stuff because those are only the processes within the container. I can't see the entire system. And there's an etcd process running here, and then just the Mesos agent, or executor is what it's called, the monitoring thing. So let me kill this one, pit 12. And I got kicked out of the container already because it immediately exited because I killed the process. So this is obviously bad, right? I killed one of the 3 nodes that store all the data for Kubernetes. But what I just did is I removed the filter that only shows actively running containers. And now you can see there's the etcd0 that I just killed. But there's a new one already running, etcd0 peer, that it spun up within seconds. So without this level of automation, this would have been, a couple of minutes until someone gets the page, a couple more minutes until they get out of bed and get in front of a computer, a couple more minutes to figure out what the hell just happened. Happened within seconds, and nobody had to get paged. Same IP. Yep, that's right. So this is important, right? So this thing obviously has state on disk. It's a database essentially. So the scheduler will try to just restart the container on that same node because there's state on there. Does it too, yeah. But not with the service-specific automation. So Kubernetes can restart containers when they fail, but when an etcd node fails, you actually have to run some commands to fix the cluster again. That's true, which is super useful for microservices, right? But for a database like etcd, you cannot easily dynamically just scale it up and down, right? So for the question was what happens if the process is just not responding? That's what the green dot is for. So there are health checks that are configured for all these nodes. You can specify an HTTP health check, a TCP health check, or run your own command, which if it exits 0, it's healthy. If it's non-zero, it's not healthy. And then you can specify what should happen if the health check fails. You can say just alert, or you can say after it fails 3 times in a row, restart this container. Yeah.
So I have one question. We have Kubernetes like mainline services here in Google, and we can take a cluster and build out and this is the third way, right? So which one is the best one?
So is the question which is better, Google's Kubernetes or Dcos? Yeah, so yeah. So Kubernetes or any other workload managed by a cloud provider, it's obviously super easy. But if you need to run on more than one cloud provider or data center and cloud, it's just not an option. Yeah. Or hybrid, right? Yeah. Yes.
I want to compare this with Cloud Foundry because there seems to be some overlap in terms of the functionality provided, like scheduling centers, centered applications, and scaling them. If this is a use case where you need to use both of them, would Cloud Foundry leverage Dcos or Dcos Cloud Foundry, or what's the best scenario of how they work together?
Yeah. So the question was, how would I use Cloud Foundry and Dcos together? I'm not an expert in Cloud Foundry, but what I see when people already have Cloud Foundry deployed, they often add Dcos to run the stateful services, like Cassandra, Kafka, and other stateful workloads. No. All right, so we showed, I did some damage in the cluster. We saw how it recovered, self-healed. Next thing I want to show, common ops task and kind of a pain to do, is an upgrade. We're running a lot of stuff here, right? It's a lot of nodes. And so how do you do an upgrade of all this, right? Usually that's something you have to figure out yourself, build the right kind of automation around it. But it's already done for you if you're running Kubernetes on Dcos. So if you remember, I installed a slightly outdated version earlier on purpose. But to update to the latest version, it's again a single command. So it's a Dcos Kubernetes update, and you just specify the package version. So let me kick that off. So just confirms you're about to start an upgrade from version 1.11, 1.10.4 to 1.20, 1.10.5. The first version, by the way, it's our internal package version. The second version number after the dash, that's the Kubernetes version number. All right, let's kick this off. So this is going to sit and wait for it to finish, and we can go over to the GUI and see how some things are happening. So you can see there's one thing that got killed. That's the application-aware scheduler for Kubernetes. So that's the initial process that came up first earlier. that one gets restarted first with the new version. And so this thing is now going to look at the cluster and restart components one by one. We can look a little bit, look at the logs too, so it'll tell us what it does. So you can see it's killing an etcd peer. It's printing some status updates. It's working. So things are happening. You go back to the list of tasks. We should see a couple already that get restarted. Yeah, you can see this first etcd peer was killed. Now a new one is running. Now etcd1 gets killed. We should see a new one pop up right here. So it's just going to roll through the cluster, again, using a plan, just like we saw earlier for the initial deployment. There's a plan for doing an upgrade, which may be different, right? Important example here is I always use HDFS as an example. So HDFS has a primary name node, which HDFS is a file system. So when you bring it up for the first time, you have to format the name node, just like you format any other file system. But let's say you lose your primary name node, you want to bring it back. If you would use the same plan, you would run this format command again, which obviously would delete all your data, right? So you don't want to do that. So that's why recovery, upgrade, and initial deployment plans are often different. There was a question here. You had a question. Mm-hmm. The question was, when do those messages get cleaned up? Good question. There's a garbage collection process that runs at some point. I don't know how often.
So you don't want to stare at it for a while.
Yeah, this is sorted by time, right? So newest is on top. But yeah, I honestly don't know when it times out. Yeah, so the question was how do you set the health check? Let me show you while this is happening. So let's say you want to run your own container. Let's just do a single container so it's easy. Let me see if I can do this off the top of my head. So I'm going to use the standard Python image, and I'm going to run the built-in Python web server. I think this is right. So this is just running a Python Docker container from Docker Hub with the built-in Python web server. And then what I can do here is I'm adding a service endpoint. So let's call this HTTP since it's an HTTP server. And then when I go to health checks here, I click add health check. Select protocol, this is an HTTP server, or you can do a command. You select the endpoint, I called it HTTP. Path defaults to /, but you can do /health, depending on your application. And that's all you have to do, really. There's some advanced settings you can do here for around the timing. Grace period is useful if your service has a long startup time and you want to run the first health check after, say, 5 minutes. Interval, how often, timeout, and max failures. So if it reaches max consecutive failures, it'll kill that container. By the way, anything I do in the GUI here, we love infrastructure as code, right? So you can kind of use this to generate a config and then check that in and version it and edit it there. The question is, are there any scenarios where health checks pass and the application is still not responding? Yeah, so it's always possible, right? Systems do weird things. But there are a lot of different kinds of health checks. So it catches a lot of stuff, right? So this, what we just looked at, is an application level health check. The process itself gets health checked, right? You don't have to define that yourself. If for some reason the container just gets killed, like I did earlier, That's not a health check I had to define. I think processes that get killed automatically get restarted. Dcos itself has a number of health checks built in, actually, so you can look at the different components. So it health checks itself. There are also heartbeats between the master and the agents, so if you lose entire machines and that times out for a while, workloads will move somewhere else. So it really covers a lot of ground. Yeah. Yeah. So the situation was that it ran out of memory or exhausted all the memory. Yeah, so that also gets taken care of. So the memory settings that you make here, I should bring this up again. So you can set your memory for this container and CPU shares. So if it uses more than the memory that you allocated for this container, it will also get killed. So useful for those things where you have a web application and you have this one method that when you call it, it blows up the memory, and that happens once a day. It would just restart the container. There are custom health checks, yes. So a custom health check would work like this. In your container image, you put in a command that does whatever you need to do. And if it's healthy, it should exit with exit code 0. If the service is unhealthy, exit non-zero. It'll report what exit code it was, actually. And then you go here, you add a health check, and you say command, and just specify, my health check command -- timeout, whatever you need to do to call this thing.
Yeah, I've done that with like web applications where you're looking for that weird scenario, like a standard HTTP check. Hey, the web server's still running, but it's not giving the users what they want.
That's
so
right.
In the script, you're like pretending to be a user, or you're looking for specific output that you would expect from a user interaction, and when you don't get that, you have non-zero exit, and then.
Exactly right. That's a great way to use this to do kind of a multi-step. Yep. Great example. All right. Let's see here. I think I did something wrong with my Python process where I wanted to show the health check. It's still deploying. Probably the container image was wrong. Okay, I think this is sort of the gist of what I wanted to show. There's a lot more things. I can go into how you access logs, how we access metrics, but I feel like I've been talking for a long time and I don't want to keep you here forever. Debugging of applications? Yeah, so how to do debugging? It's to do debugging, I would do essentially what I did earlier for killing etcd. Let me start somewhere else, actually. This update finished, by the way, so we now have, let's look at this, kubectl get nodes. Yep, and you can see version 1.10.5. That's the version we wanted to upgrade to. So we have an upgraded cluster now. All we had to do is run this single command. Let's see if our workloads are still running. Yep. Still have those 5 pods that were running earlier. So that was cool. Debugging, yeah. So different kinds of debugging. There's a tab here that basically helps you debug misconfigured containers. Let me see if I can simulate that, actually. Just do this real quick. So what I'm going to do here is I'm going to start a container, and I'm going to ask for 32 CPU cores. I don't have a machine this big in the cluster, so this container cannot start. And so to debug this, we have some tools here. It's going to take a little bit, like a minute or so, until the debug info will show up. That's already here. So I mentioned this resource offer model earlier, right, where the system offers what's available to the applications, right? So in this case, Dcos will say, let me look at the nodes actually. So we have nodes that have details. So we have 8 CPU cores on those nodes and 28.4 gigs of memory, 113 gigs of disk. So no node is big enough. So this is what the system is offering to this container that I'm trying to start now. It says 8 CPUs, 8 CPUs, but the container asked for 32, so it doesn't start. And you can debug that here. So it says there's been 11 recent resource offers. Just tells you what's happening, right? It waits for those offers to match. And then it says here, shows you all the offers that came in from the different hosts and which different types of resources matched, right? So all the ones except for this node matched on the memory size. They all matched on disk size. They all have the right ports, but none of them have enough CPU, right? So that's how you can debug when things don't start. And application level debugging, I would basically do what I showed earlier. Dcos Task, let's look at everything that's running. And so let's pick one, maybe pick a Cassandra. I'm going to use the container ID here. And I would do Dcos Task exec, IT for interactive and open a TTY, container ID, and bash shell. So the last piece here is just a command. So you can also do ls or whatever. So again, you're in the container and look at what's on disk, what's running. I don't know, GDB. I don't know if it's in there. Nope. But you would put your favorite debugging tools in your container, or you could copy it in the container also after the fact, and then it's essentially like being on the machine, but you're in your isolated container. What's really cool here too is to do this Dcos Task exec that I just did, I didn't have to give anybody SSH access to the machines. This all happens through an API that's managed by Dcos and that's access controlled by Dcos. So you set your permissions at the cluster level, not on an individual machine level. Let me show you what that looks like. So you have users and groups here. And then you have these permissions. And you can, for example, say, for my services that run under Marathon, that are under the path production, this user gets, create, read, update, delete. So different users can get access to different types of applications.
Question.
Mm-hmm.
When there's port conflicts,
Mm-hmm.
can you resolve those automatically, or do you have to go through the same process?
Yeah, so to resolve port conflicts, great question, common problem. So you can, or by default, Dcos gets certain port ranges on the machine that it will manage as a resource. You can configure what those are. And so when an application requests a port, which you can do in here on the networking, there's different networking modes here. There's a virtual network, bridge networking, or host networking. And so I can ask for port 80 here, right? This will only launch on a node where port 80 is available. Dcos will take care of that. So it's managed, the ports are managed just like other system resources, just like an amount of memory. Those ports can only be consumed by one application, if they're managed by Dcos, right? Dcos doesn't get all the ports on the machine. So there's other stuff running too.
Yeah, so you have several layers of abstraction built in,
Mm-hmm.
right? And containers do this all.
Mm-hmm.
Containers can run perfectly any port and then expose and everything.
Mm-hmm.
And even then, that particular port
Right.
So in some ways, I'm a little surprised that that's not more abstracted, where ports should never matter, and external ports.
Yeah. So the question was, why, if there's so many layers of abstraction, shouldn't ports be abstracted more? They can be, and it's this checkbox that's checked by default. Assign host ports automatically. So I'm just saying I'm running a service that I'm calling HTTP. It's just a freeform text field. And this field here is disabled, so it'll just automatically pick a port if this is checked. It picks the port that's available, and it'll expose it as an environment variable called port 0. Or the first port actually just becomes the environment variable port, which a lot of applications look for automatically. So you can just do that. And this is for host mode, by the way. So different networking modes here for containers. Getting into the details now. So host networking means the host network interface is shared with the container. It's the same network interface, so any ports that the container uses have to be available on the system. That's not the default in Docker. If you look at a lot of Docker tutorials, the default is bridge networking, where the container gets its own network interface that sits behind the bridge, and there's network address translation. So you can use whatever ports you want in the container, and then the container runtime matches, say port 8080 in the container to port 80 on the host over a bridge interface. Obviously, now you have that bridge interface that causes, there's a performance hit there. And it's also a problem for distributed applications that advertise themselves to other nodes. They will advertise that NAT IP that sits behind the bridge, which obviously doesn't work. So not really a fan of bridge networking myself. We default to host. And then there's virtual overlay networks too. Yes?
Can you elaborate the differentiation then of DCOS is doing versus the bridge network? Because I for some reason, always thought it was bridge network.
Yeah, so there's 3 different networking modes here, right? DCOS defaults to host, which is really, you have a NIC on your host, and when you start a container, it's basically what the process that's running in the container sees the NIC the same way any other process in the system would see the NIC, right? It's just, it's not in a different namespace, right? Part of what containers do is they have a network namespace. In this mode, the network namespace of the container would be the network namespace of the entire system, so it sees the same interfaces. So that means if you're running 2 containers and they both want port 80, it doesn't work. There's only one port 80 on the machine, right? So that's host networking. It's the most performant one. And also a good fit for distributed systems that advertise themselves because they will advertise the actual IP of the host NIC. Bridge networking means every container gets its own network interface, and then the container runtime manages a bridge that does network address translation. So you have containers that get 172.16.01, 172.16.02, and so on. The bridge has a gateway IP for those containers, and the containers never see the host interface. So
And again, we can create our own bridges with a separate network interface.
you can create your own bridges too, that's right. So benefits, you can run as many containers as you want with port 80. They can each bind to port 80 because they have their own IPs behind a NAT. Problem now is, how do you talk to those guys from the outside? You need to do port mapping, right? So first container gets 8081 on the host. Next one gets 8082 on the host, right? So you still have to do that. I'm sorry?
Is there a service that does that for you?
There is a service, so there is a service that, not that specifically. There is a service though that does service discovery. So I can show you that here actually. So, and it works with bridge networking too. You would just have to put in your container port, like let's say I'm binding to port 80, put in there. But bridge networking doesn't really give you much in this case, except that, I mean, you can write containers that always bind to port 80 instead of telling them to dynamically look for port. But so here, if you check this box here, enable load balance service address, and let's say I'm giving this a port 80. It's really hard to see, and I didn't give this thing a name. My service. Apologize for the light gray fine print. This might be a little better. So the DCOS layer 4 load balancer and service discovery network that I talked about earlier, if you check this, what it will do is it will create a mapping from a virtual IP that it allocates for this service that will stay constant for as long as the service is running. It'll resolve this host name here to that IP address, and it'll intercept any packets to that virtual IP on port 80, and then do the mapping to the actual host and port endpoints in the cluster, right? So if you have a client that talks to this service, this is all the client needs to know, even when the containers that make up the service move around between different hosts. This doesn't change. And they could be running on, port 1024 on one node, on 1025 on a different node. This is the only thing the client needs to know. Mm-hmm. Okay. Yeah. Mm-hmm. Yes.
So you showed us building these canned containers.
Thank you.
You showed us debugging a little bit.
Yeah.
So now the world is kind of never works like that. I get that, I find the bug, now I fix the bug.
Yeah.
Right? I've patched Cassandra, right? How do I get my patch into this system? How do I rebuild that?
Yeah. So if you need to patch applications, so there's a couple ways. Depends on the application. So for workloads in the catalog, right, the community behind Cassandra, or the company behind DataStax, the commercial version of Cassandra, they release new versions all the time, right? So say something's broken, okay, is there a version here that fixes my bug? You can see there's quite a few versions that get released, right? And then you just pick the right version, you do an upgrade like we did earlier for Kubernetes, upgrade it that way. For your own workloads, your own containers, your microservices or macro services, you do a deploy here, right? So let's go to this Python service that I tried to start earlier that's still not coming up. Containers have version tags, right? So after the colon here is a version. So the 3 is a terrible example. Don't do that. It's just the version 3 Python. So it could be 3.6.4. It could be 3.7.0. I don't know. So what you should do internally, for your own applications, I like to do 2 things. So you either, let's say the application is built off a specific SHA, then put your git SHA in here as the version number. And developer fixes the bug, runs through the CI/CD pipeline. Now there's a new container with the new SHA, and this is the SHA that fixes it. So go in, put in the new SHA. Review and run. Sorry? Great point. So the way to work around that is you version your containers with build timestamp or build ID, something that your build system generates. That's the other way to do it, yeah. Personally, I like to use timestamps most commonly. Yeah, build timestamp.
I want to come back to the Cassandra one. Let's say either I'm not allowed to upstream my patch, or Cassandra is not getting around to putting my patch in.
Yeah.
How do I take that prepackaged container?
Yeah. So this is where it gets a little more tricky. Then you go in, you find this repository, DCOS Commons, which I think it has Cassandra in there. Yeah. So you fork this repository. You go in. This is one of the main configuration files. And I think it's not this one, but there's a file in there that specifies the container version. So instead of using the one that the official package has, you point it to the container that you built that has your code with your patch in there. And then you add now your custom Cassandra package to your own custom catalog, and then you deploy that instead. So you would go in here, you make there's instructions online for how to do that. You build your own catalog instance, and then in settings here, this points to the official universe.mesosphere.com, but you just add your own URL, myuniverse.mycompany.com, where you have your patched package. How much effort is there to build a package? It depends on the software that you're trying to automate. Yeah. Mm-hmm. What is the effort for building a package? Are you talking about building it from scratch or doing a patch? Yeah, I mean, doing a patch is not that hard. I mean, you can see this is the main configuration file here. There's a lot of variables. I mean, it depends, right? Do you know how to fix the bug in Cassandra? That's probably the biggest problem. Yeah. Yeah. So, I mean, the first thing I would try is see if they fixed it in their package, because there's a DataStax package here too, DataStax DSE. So, different versions here. You get a bunch of hot patches. Yeah. Mm-hmm, mm-hmm. Yeah, I mean, the effort would be you build Cassandra, which you're probably already doing. You build a container that includes this Cassandra, or in fact, we might actually be pulling it down with a URL here. Let's see if I can find that real quick. Let's see, URL. So there's two ways to build these packages. There is one where you point it to a container that basically has all of your code built in. And there's another one where you point it to a base container that, for example, could have just your JVM. And then you can add artifacts at runtime. So you can say, all right, use this JVM base container, and at runtime download this Cassandra artifact that I'm storing in Artifactory or something. So if you had to maintain your own fork, your own version, that's probably what I'd recommend, because you would essentially just change that URL to point to the new patched version, rebuild this catalog package, and then redeploy. Yeah. Yes.
So DCOS is running on a bunch of workloads.
Mm-hmm.
And how it actually manages the workload itself and workload load itself?
How does TCS manage the workloads? And what if a node fails? Yeah. So how it manages the workloads, there's a lot to talk about there, broad topic. But essentially, there's an agent on the node. There's the master node. And then there's multiple of these schedulers that I talked about, right, for each of the workloads. So let's say scheduler decides, let's pick an easy example, right, the Python container here. So you told the scheduler, run this Python container, 1 copy. Give it 1 CPU core and 1 gig of RAM. The scheduler then waits for the master to send it an offer that matches this requirement, right? 1 CPU, 1 gig of RAM. Then it sends a message to the master saying, here's my spec for this container. It's this container image, these are the resources, environment variables, and so on. And launch it with this offer. And the master then goes to the agent that the offer came from and says, here's the spec, please run this. And the agent goes in, creates the container, which simplified a lot. It's basically 2 steps. First, it's getting the container image, creating a file system from that container image, and then creating the C groups and namespaces, so the Linux container itself. Once that's created, it'll start the process in that container, and it'll monitor it. So that's the rough high-level workflow. When a node fails, there's a couple of things that can happen, right? So a node can go away because you're patching the kernel and you're just rebooting the machine, right? So we don't want the system to think that this node is, burned up in a fireball and never comes back, right? So there's a certain timeout where the system says, all right, I'm going to wait if this thing comes back. Now, once that timeout expires, it really depends on the workload, right? So for the stateful workloads, we don't want to do, what was it called earlier, death by automation, right? We don't want to over-automate all the things because there's a lot you can do wrong there. So the schedulers will actually, for stateful workloads, don't take automated action. But as an administrator, it's only a few commands to say, look, this node is dead. Go find another one and run there. So you'd run that command, but you have to say that explicitly because it's such a potentially dangerous operation. For stateful workloads, they will just go to other machines that have the right resources available.
So what has been done on that particular node? Like, is the node data static actually?
How would it recover? Mm-hmm. So let's say you're running something stateful on there. So what? Let me see if you can see that in the GUI. Files. Can't really see it, but so stateful workloads use a feature in DCS that we call local stateful volumes. So any data that it puts on disk that it wants to be persisted, right? Containers always get an ephemeral file system that only exists for the lifetime of the container. But if they want to store persistent state, they can create local persistent volumes. So it's either a local disk or a path on the local file system that we treat as a persistent volume. So DCS will track that even after restart, right? And so when the node restarts, it rejoins the cluster. It says, hey, I'm agent, with this ID. I'm back. And the scheduler, the Cassandra scheduler says, hey, I know this agent. I know I have data on there. So it'll try to relaunch on that node. So it'll say, I want to run this container on this node again with this ID and using the volume ID such and such that I created earlier. Agent, the volume still exists, so it'll just restart the container with that same volume. Data still there. So you don't have to copy it around the cluster. Mm-hmm.
Just get one more question.
Yes. Mm-hmm. Yeah, so DCS is everything is HA. There's multiple masters, multiple zookeepers which store the state. Yeah. You can recover the entire DCS. There's also a backup and restore command, so you do an offline backup if you should, everything burn up. Yep. You had another question. Yeah.
So you mentioned that you got that disk locally.
Yeah.
But what if before my workload get put back on there, all the CPU and RAM get sucked up by other workloads?
Mm-hmm.
Can that on-disk workload be farmed out via an NFS export so another node can then see it and just use it?
Uh-huh.
Shouldn't storage also be ephemeral?
It's not how I would solve it, but there is external storage. Yes.
Can I run an NFS
You can. There's
node on every single thing and just have all ephemerals be available everywhere?
external volumes too. Yeah. So they're exposed.
Inside the nodes.
And just pretend like it's local storage?
That way, like, my storage becomes a thing I offer out.
You could. I wouldn't recommend it. Because a lot of these things are built for local storage, like Cassandra. They would think it's local, but you shouldn't, pretend like it's not local.
There's one system that does that called MapWire. They have their own.
Yeah, there's storage systems that do this, but Cassandra and friends are really built for local storage, so that's what I would do. But to your question, right? What if other things run there and claim all the resources? You can make what we call reservations, so you can ensure that certain workloads get those resources.
Okay, so the next question I have is, so like we have a problem with Kubernetes at work right now where if we have, it doesn't hurt us so bad in production because we have 3 of anything and we can say, oh, take that 3 and upgrade it, it goes 3 to 2 to 3 to 2 to 3 to 2 to 3, and everybody's happy.
Mm-hmm.
But if we do it in other places, it says, oh, you want to go from 1 and you want to upgrade to 1, and its path from 1 to 1 is not from 1 to 2 to 1, it's from 1 to 0 to 1, and we have to suffer an outage. What does this do when it goes from 1 to 1?
Like one etcd?
1 to 0 to 1, or does it go from 1 to 2 to 1?
That's a good question. I don't know. Alrighty.
Okay. This has been a fun talk.
Thank you.
Everybody thank Tobi for giving us a great
Thank
talk.
you.
Next month, we're going to have the Storage Network Association here to talk about redfish and swordfish. Thank you all for coming. I think you all need to eat 5 slices of pizza, so if you haven't met your quota, we need to get rid of that, so please
And
help
the beer,
us.
too.
Beer, too. You don't have to leave right now. We're still packing things up. Feel free to talk, and thank you for coming. See you next month.
Thank you for listening. Thanks for all the great questions. Thanks. This was fun. Lots of great questions. And more questions. We'll need beer first. Is that okay? Something else. I forgot.